Greetings, everyone. It's another Friday afternoon here in Hawaii. It's looking pretty nice out there. But I'm really excited to be in here with you because today I'm going to be talking about API design. And this is API design is in many ways design when you're talking about computer software. If you can get your APIs correct, then you probably have a good design. If your APIs aren't correct, then you clearly don't have a good design. And so one of the great things about the project that we'll be doing this semester in the class, and that I'm going to be focusing on pretty much for the most part today, is the fact that it's going to require you to think hard about APIs. And I think that's a very important skill to practice in getting better as a software developer. And so I'm excited to have you check it out. So let's get right to it. The first thing is what an API is. API stands for Application Programming Interface. You've been using them forever. You may not have thought of them as an API, and you may not have ever really thought consciously about designing your own API, but you are going to be familiar with them. In general, it just means an API specifies a boundary between one program or one component of a program and another program or another component of the same program. And by boundary, what I mean is it's going to tell you kind of what you have access to, what's allowed, what you can manipulate, and what you can't have access to or do or manipulate. And that's an essential part of abstraction, and that's also a way that we create programs that are simpler, because by defining boundaries and specifying things that you can't do or manipulate or know about, then it requires you to understand less about that particular area of the program. So the two key things to think about here with boundaries is that we can have boundaries within a single program, and we can have boundaries between two programs running on the same computer, or even two programs running on separate computers. So there's a lot of advantages to having APIs. Let's list a few. The first is that by creating these boundaries, you develop a partitioning of your overall design, and that makes things simpler because you can see where the boundaries are. The second thing is that once you have boundaries, the things that are kind of behind the boundaries can generally be changed without impacting upon other parts of the program, or at least it's easier to do that. When you make a change in one area of your program and it has repercussions throughout the entire system, excuse me, that's called the ripple effect. Okay, you think of a stone being tossed into water, and then it kind of the waves ripple out from that and spread across the entire pond or for very far away. The idea is that with a good API, there's lots of things you can change within a particular component of your system without making other parts of the system fail. Okay, some APIs aren't designed to well, let me put it this way. With any API, there are going to be hopefully there will be certain changes you can make without a ripple effect, but also for any API, there's always going to be certain kinds of changes which are going to produce a ripple effect, and in fact, certain kinds of changes which are going to force a change to the API itself. Okay, so anytime you draw a partition, you're hoping that that's the right way to draw that partition, or the right place to put that boundary to maximize the simplicity and understandability and maintainability and evolvability of the design. But that may not be the best place, or there may be some unforeseen thing that you try to do in future where you didn't anticipate it in your API, and it causes lots of problems. Okay, so there's certain kinds of changes that you should be able to do without a ripple effect, but not every change can be done without a ripple effect. Third thing is, this is quite important and something that we want to be able to pursue in our class, is that once you have a boundary, if you specify it in the appropriate way, it enables different people to implement different versions of that boundary and enables you to try out multiple ways of doing things. And that's what I'm going to show you today, is a simple little program I built which allows exactly that. And I think that'll be kind of cool for you to see how you might do that in Java. Then finally, having good boundaries enables development to scale, so that you can have multiple people working on multiple pieces of the program at the same time. And once those boundaries are established, they know how they interface to other sections of the program, and so they can write to that interface. And the implementation of that interface may not even be completed yet, but they're still able to write to it because it's been specified. And so that allows the overall development project to be broken up into pieces which can be worked on by individual projects, enabling the entire team size to get larger. Also allows people to work on things at the same time. Now, APIs have overhead as well. Okay, so all of these good things I've talked about in the previous slide also, in some sense, directly lead to some of the disadvantages of APIs. So let's look at that. The first thing is that for small programs, sometimes creating an API is overkill. And to a certain extent, when you look at my sample program today, you're going to go, I don't know, like, why do we really need all that extra? We're going to see some duplicate classes, and we're going to say, boy, that looks redundant and kind of complicated to do things that way. And that would be exactly right. APIs do have a cost. You don't get all those things I showed you in the previous slide for free. So there is a certain amount of complexity that you can add, that often is added to your implementation in order to achieve these advantages. The second thing, as I said before, boundaries are good in some ways in that they enable certain kinds of changes to be made more easily, but boundaries are bad because they make other kinds of changes harder to accomplish. Specifically, changes where you need access to something that was formerly hidden behind the boundary. And then finally, if you're really concerned about performance, oftentimes APIs introduce certain kinds of abstractions or certain kinds of performance overhead that may prove to be a problem. So generally, the process of optimization oftentimes is the process of removing abstraction from your system and more tight coupling of components in your system. If you really need the performance, that's generally the kinds of things you try to do, aside from the normal things of like picking a better algorithm and so forth. But structurally, if you find that your performance problems refer to structure, then increasing coupling is the kinds of things that can often help. Now, remember that coupling is generally a thing that you want to reduce in a system, okay? And APIs are a way of producing loosely coupled systems, which for maintenance and understandability and evolvability, low coupling is generally considered to be a good thing, okay? But I just want to note that with respect to optimization, coupling can sometimes be a problem. I'll say in this class, the overhead involved with the interfaces that you're developing for this class are almost certainly not going to be the cause of any performance problems. You may have performance problems, but it's not going to be because you had an API. Okay, so as I said before, there's a couple kinds of major kinds of APIs. APIs that occur within a single program where you're separating out components and generally establishing kind of public and private packages or areas. And then there's APIs that occur between programs, and those are more generally referred to as protocols because what they basically specify is the way that communication occurs from one program to another. Okay? So an example of an in-program API is the collections framework in Java. So you have a lot of interfaces. So here's an example of a portion of the collection interface. It specifies a bunch of operations that any collection object should be able to perform. Add, clear, equals, is empty. But it does not specify in the interface exactly how those operations are implemented. Okay? And then you can have a whole bunch of classes which all provide various implementations of those particular operations. Here's an example of the Java docs for the collection class, and you can kind of look through that. The collections framework is in generally an example of a pretty well designed API. There was a lot of thought that went into it and very good people working on it. Joshua Block, who's the author of Effective Java. And so if you're interested in high quality design and high quality APIs, you might want to take a look at this. Now, as an example of between program communication, this is a reference to a topic that we've been talking about previously in the class, which is the REST, representational state transfer architectural paradigm, because that is an example of an approach to specifying a communication protocol between different components. And we've been doing that so far this semester, is writing clients and servers that use gets and puts and appropriately specified URLs to communicate data back and forth. So I just wanted to show you an example of a protocol for a program that you're probably most of you are familiar with, called Twitter. And it's pretty neat. I'll show you kind of an example of the web page you can get. You can, if you Google on REST space Twitter, or Twitter API or something like that, you can get to these pages, and it shows you how they've constructed a RESTful interface to the Twitter system, which enables you to write code that can go and post tweets and get the timelines and find out about users and so forth. There's, in terms of specifying the REST, the RESTful communication protocol for the Solar Decathlon system, you're going to be using Google Project Hosting. And so I wanted to point you to a wiki page for the Watt Depot system, which is a system that's been developed in my lab, because it specifies a REST API for the Watt Depot service. The actual API itself, the specifics of the REST protocol for this system, is not as much interest actually as simply seeing how using Wiki, the Wiki mechanism in Google Project Hosting, you can build a page that specifies a RESTful protocol. Okay, so I think that might be helpful to you. I just wanted to mention it here. You can go look at it. I personally think this is a reasonably good RESTful API as well, so you might get some insight from it. Okay, so now let me get to the object of why you care about APIs and the way you're going to be working at this semester. This is kind of an high-level architectural view of the Solar Decathlon iHale system, or the software for it. And as you can see, on the left-hand side, we have a bunch of systems that will be running in the house, such as photovoltaics or air conditioning, heating, aquaponics system, and so forth. And they'll be all attached to sensors which can send data over HTTP to the iHale system, where that data will be stored. Okay, and then on the right-hand side of the system, you can see that there's additional kind of peripherals that can be defined, like a tablet computer or smartphone or even a Facebook interface, and that can also, request data or even maybe send data to iHale and interface again with it over HTTP. Then if you look at the middle box, you can see that the iHale system itself is composed of three components: a web-based UI, which we all know will be built in Wicket, the web framework that we all love. And then in the middle, you see this thing called iHale API. And then at the bottom, you see a repository box, which is going to be, implement the storage for all this data that we'll be sending back and forth. And the repository box will be implemented using Berkeley DB. Okay, so what's kind of cool about this system is that this system has both kinds of APIs that need to be specified for it. So on the one hand, the communication between the house systems in iHale or the optional interfaces in iHale uses HTTP. That's going to be communication between different programs, between a tablet computer and the computer that runs iHale, or between the aquaponics sensor that'll be connected to the network and iHale. Okay, so for that, we want to specify a RESTful API. On the other hand, within the iHale system itself, we have 3 components, and they need to communicate with each other. And so we need a within program API as well. Okay, so this is kind of, it's a relatively complicated system. We need to be able to have people be able to write on, develop different components at different times and not step on each other's feet. So we need some way to kind of partition things up. So we'll be building a RESTful API or designing a RESTful API that will specify how data is sent and received between different programs. And then in the inside, we'll be developing an API in Java that enables us to specify how the different components of the system inside are going to communicate. Okay, so let's go off to the demo. And in order to show that, let me first take you to the ICS Software Engineering Examples Google Project Hosting site. And what I've done is I've implemented this little program called API Contact DB. Now remember that there was a RESTlet contact service, which I then transmogrified into a persistent service called Contact DB using Berkeley DB. And what I'm going to do now is I'm going to alter that. I've altered that code base and created a new project called API Contact DB, which kind of illustrates how you can create an API in Java. Okay, and we'll see what that looks like. So you can download this code and unzip it, and you might get a directory that looks something like this. And so we can, as usual, we can type ant and make sure that everything works, or actually even better, ant-f verify, which is going to run our quality assurance tools like checkstyle, PMD, find bugs, and JUnit, and hopefully everything will work okay, and it did. So everything's all good that way. And the second thing I guess I'll do, just to remind you of how this Contact DB thing works, if you don't remember it, you may want to go back to the previous screencast where I talk about the Berkeley DB system and listen to that just so you get an overview of what this thing does. But I can do ant-f jar.build.xml and build a jar file. And what we can do with this jar file is it allows us to persist and add various things to a persistent database. And so if we say java-jar API contact DB, and we don't provide any arguments, let me just check. That's a little strange. Okay, sorry, I had a typo in my build file, which I've now fixed. So if I go ant-jar like I did before to build the jar file, and then go java-jar API.contactdb.jar, just like I did in the Berkeley DB Contact DB system. I get this usage explanation, and so following that, what I can find is that I can put a name with info about them and a unique ID into the database. Okay, so stored in the database closed, so it's a persistent thing. Then once I've done that, I can type get, and now I can see that particular record about me was retrieved from the database, and then I can do things like, say, delete, and then if I do a get again, I can't get it because it's been deleted. Okay, so that's like completely uninteresting, right? And that's not the point of this lecture. The point of this lecture is to say, let's say that we weren't sure which kind of database that we wanted to implement. Maybe we wanted Berkeley DB, maybe we wanted MySQL, maybe we wanted Derby. Lots of databases out there. What if we wanted the flexibility to write a bunch of code without having to commit to a particular kind of database. Remember that Berkeley DB is an object database and MySQL is a relational database. Okay, so wouldn't it be cool if we could abstract away and not even care what kind of database we were actually using underneath the covers? Okay, so that's a neat thing, right? You'd love to be able to build a system and say to yourself, you know, at this point in time, I'm just not sure what the right database I should use should be. So what I'll do is I'll build an API that enables me to abstract away the details of what kind of database I'm using, and instead just get on with my programming, use, you know, Berkeley DB or whatever to begin with, and defer and yet allow myself the flexibility to change later on. So let's see how we might do that. Okay. So what I'm going to do is go into Eclipse, and I'm going to import the whatever it's called, that API Contact DB project. So you can see it's here, and I'm going to type finish. Okay, here it is. Okay, now things are going to be a little crazy here. This is going to look a little different from what you're used to, and I'm going to try my best to explain why things are the way they are as we go through this. So the first thing you're going to see is that there's actually 3 source folders for this particular project. There's a source folder called source-backend, a source folder called source-frontend, and a source folder called source-API. Okay? Now the basic idea here is that our API is going to separate our back end from our front end. Our front end is going to be is essentially what you saw me typing to the command line. It's going to be the code that implements the little client, okay, that you can get stuff from the user and put and get and delete. Okay? The back end is going to be a specific implementation of a persistency mechanism, in this case Berkeley DB, because that was the convenient one, I had it lying around. Okay, and the API is going to be some special code which is independent of both of those things, but enables them to glues them together. Okay, so let's first of all look at our API and see what that looks like. Okay, and what that looks like is it consists of 2 classes. The first class is called contact.java, and it's a vanilla Java class that specifies contact information. Okay, and you can see there's nothing special about it. It does not, for example, have any annotations for a particular database manager like Berkeley DB or whatever. Okay, so it does not have any dependencies on any specific implementation of a repository. Okay, the second class, well, it's not really a class, it's an interface. Okay, it's a Java interface called ContactDB, and it specifies 3 methods: a get contact, a put contact, and a delete contact, where the contact object that is returned by get contact is this vanilla looking thing that's also part of the API. Okay, so you can see that our API consists of a class where we get and put objects, and the API can also consist of the objects themselves that are passed to and from and through the API. Okay, so there's not really much to say here, right? We got a get, put, and delete, and the kind of object that we're getting, putting, and deleting is this contact object. Okay, now let's look next at the front end. Okay, the front end has this thing called contact client, and this is going to look very much like the contact client from the persistence lecture where we were talking about Berkeley DB. And so I'm not going to actually go through the I'll go through the whole darn thing because it's 15 lines of code. Okay, so we have this main class. That's what's invoked when we invoke the jar file from the command line. If we don't have any arguments, it's going to give us a little details about that we can do puts and gets. And here, these 2 lines of code are the 2 lines of code that we're inserting that are different from when we had our former example, which didn't show this API. what we're going to do in these 2 lines of code is create an instance of a specific implementation of our ContactDB class. So here's an interface right here, okay? And then right here, what we're going to do is we're going to say, I'm going to take a string that specifies the fully qualified name of a class that implements ContactDB, okay? And once I have that string, and I'm making a string here, and I'm hardwiring it in here, but you could be asking for that from the user. You could be reading that in from a properties file. You could be getting that from a RESTful request. All sorts of crazy stuff. You come up with this string somehow. Okay. Then you do the following bit of Java magic. Okay. Basically, you call the forName static method of the class, passing it that string right here, okay? And that returns the object, which is the representation of that class, that Berkeley DB ContactDB class, okay? And then we say, give me an instance of that sucker. Now I have an instance of the Berkeley DB ContactDB class. And what I'm going to do is because of the vagaries of Java, I've got to cast it to the ContactDB interface, and then I can return it without any problems. And now I've got this object called DB, which is an instance of the ContactDB class. Now it's actually also an instance of the Berkeley DB ContactDB class. Okay, but we're going to make it an instance of ContactDB just in exactly the same way that when you're writing regular Java code, you know how you'll write list foo equals new array list. Okay, and the reason you do that is because you need an implementation of a list, but you don't really need the specific properties of an array list for your application. So what you want to say is, I don't really need to use array list methods here, I just need a list. And so by saying list foo equals new array list, what I do is I communicate to the user, and also I enforce in the remainder of my code the fact that the only operations that can be invoked on this instance of foo are list operations, and whatever special operations are associated with array list are not important for us here. In a similar manner, the Berkeley DB ContactDB class may have a lot of methods associated with it specific to that particular thing, but really all we care about is that it implements and provides us with the ContactDB operations, which are those here: get contact, put contact, and delete contact. Okay, so that's what we've just done here, is we have created this object, which is an instance of ContactDB. Which instance is it? Well, it turns out to be the instance whose fully qualified class name is that. Now that's crazy stuff, right? If you think about it, you may have never done this before in Java. Okay, it's taken a string that named a class and converted it to an instance of that class. It's cool stuff, man. There's all sorts of great stuff you can do. This is called reflection, and you might want to read about it in your Java in a Nutshell. And I guarantee you, it really can open up some new avenues for programming. So anyway, once we have this DB object, then most of the rest of this looks just like before. The difference is that here we create a contact, and that contact comes from our API, okay? And then we use this DB instance, invoke the put contact method on it, passing it one of these guys from our API, and similarly we call DB with the get contact method. We get one of our API contact objects back and print it out. Similarly, delete contact, we call the delete contact method of our implementation of the ContactDB class. Okay, so we're calling get contact, put contact, delete contact in our contact client. I'm telling you that it's a ContactDB, but when you look over here, you say, well, where's the implementation? I don't see an implementation. Okay, this is the beauty of it. is that what we've done here is we've said, I'm going to say these are the only methods you're allowed to have, but it's going to turn out that where you find the implementation of those methods are in this class right here. Okay? So without further ado, now let's look at the back end. Okay, so just to be clear, right, we've got our contact client, which is the front end. Okay? The front end has no communication with the code in the back end. Okay? I mean, it has, at a high level, it has communication because there is this string which identified, you know, the implementation in this backend code. But that's the only place that there's a binding. Okay, and that could have been read in from a property, and you could basically, each time you run this program, you could pass it a different string, and one execution of the program use Berkeley DB, and then the next execution of the program use MySQL, if you had a MySQL implementation of this contact DB class. So there is a binding in here in some sense, but it's done dynamically at runtime. It's not hardwired into the code. Okay? So let's now look at our back end, and this is a little more complicated. Most of this stuff is going to turn out to be actually almost identical to the Berkeley DB persistency code implementation, but we've got one special class which I'm going to start with, I think, which is the Berkeley DB contact DB, which is the class that implements our contact DB interface. Okay? And so we've got to implement get contact, put contact, and delete contact, which we're doing. One of the cool things you can do in Java or in JavaDoc, which you may not have known about before, is you can notice that I have the JavaDoc specified for my interface. Well, when I get to the implementation of the interface, I may be thinking to myself, you know, the JavaDoc for this implementation of it is really, there's nothing new I want to say that hasn't already been said in the interface JavaDoc. So you can actually use this special kind of, this @inherit_doc tag in your JavaDocs to say that this particular method, if someone looks it up in the JavaDocs, will just simply display the JavaDoc associated with the contact DB class. Okay. So we've got to override. We're overriding, you know, what occurred in contact DB, and and here's where things get a little interesting. Okay, so what we're going to do. Remember that in Berkeley DB we have to annotate a class with the @entity and the @primary key annotations in order to make it persistent. Okay, and you can see I'm going to show you the Berkeley DB contact class, which has this @entity and @primary key annotations. Other than that, this thing looks exactly like the contact class. Okay, those are the only two lines which have changed. Okay, why didn't I just make it the same class? The reason why is because I don't want to, first of all, in my contact DB interface, I need to pass contact objects back and forth. I could have maybe kind of had an array of strings or something, you know, lame, okay, and not had to do it, but that would be crazy. I need a contact object, so I got to represent it in my interface. But I don't want that contact interface to have any details associated with a particular implementation of a database, and Berkeley DB requires this annotation. That's just the way it works. So what I have to do in my API is I now have to have an internal version of the contact class, which I'm calling Berkeley DB contact, which adds in all the junk that Berkeley DB needs. Okay? Here's an example of where using an API is making things more complicated. Okay, because this is almost like an extra class. We now have basically two versions of a contact class which differ only with respect to the fact that one has this, you know, database specific annotations and the other one doesn't. But that's the price we pay. Okay. So how does this? Well, okay. So that's our internal class that we're actually going to persist out to the database. Then what we have is the implementation of our contact DB interface. And so what this basically does is this calls the contact data access object, which I'm now calling Berkeley DB contact data access object, gets the contact, gets one of these Berkeley DB contact objects out of it. Remember, that's the annotated version of the contact. And then it has to return the API version of a contact. Okay, so how does it do that? Well, what I decided to do in my Berkeley DB contact object is to provide a new constructor. And what this constructor does is say, if I've, okay, I'll just tell you. What I did is in this class, I created functions to go back and forth between the two kinds of contacts. So here's the constructor which takes a contact from the API area and gives you a Berkeley DB contact. Also, I created a toContact method which you can operate. You can take a Berkeley DB contact instance, one of our database specific things, and it will return a contact object from the interface, just calling the constructor for it. Okay, so what this enables me to do in my interface is say my get contact, this contact DB interface has to return an object of type contact, which is my API contact. So in order to implement that here, what I do is I get an object, I call the get contact to get my internal contact object, and then I call the toContact method of that internal object, which returns one of these contact guys, and that's what I actually return. Okay, and so similarly with a put contact, I'm passed a contact object from the API. I invoke my constructor to build an internal contact instance out of it, and that's what I put into the database. Delete is easy because I just have a unique ID and I don't have to do any rigmarole to move things back and forth. Okay, so that's how that system works. Now, why would we go through that effort? Okay, again, to reiterate, we are building a boundary. Okay, and I'll show you just because it's cool. Let me show you the build file where what I wanted to do is illustrate that in order to compile, I first did this thing out in Ant. You probably haven't seen this, but there's this thing called a macro definition facility. So I created a macro called compile component where I could pass an attribute, which is the source directory that I wanted to compile. Okay, and then what you do is when you want to refer to it in that attribute inside your code, you use this @ thing. So you can, if you're interested, type Google on Ant space macro def, and you can see the documentation page for that. But anyway, what I wanted to show you is that if I wanted to compile the API, I can compile that without referencing the back-end code or the front-end code. Okay, so I can compile that source API without any reference to any of the remainder of the system. So one development group could be working on the API and compiling it, and no one else, they don't have any dependencies. And if you look at the code, you can see, yeah, it's obvious. The contact class doesn't refer to anything else, and the contact DB class doesn't refer to anything else. It doesn't refer to the client, it doesn't refer to the back-end thing. Okay? So what you can see if you examine the build file is the compile API field. It needs Ivy because it needs JUnit and so forth, but it doesn't depend on any other components. The front end, okay, if you want to compile the front end, it needs the API, okay, but it does not need the back end, right? If you look at the front end code, contact client. Okay, this string, that could be any string, so that doesn't create a dependency upon the back-end code. But if you look at the actual code and with respect to compiling, we do not refer to any of the database-specific back-end things. Okay? Similarly, if you look at the back-end code, there's no reference to any of the front-end stuff. Okay? But both the front-end and the back-end refer to the API code. Okay, so if we go back to our build.xml, what you can see is that if we compile the front end, we need to have compiled the API first or have access to that code. If we compile the back end, we need to have also access to the API, but the front end doesn't need the back end or vice versa. Okay. Now in Eclipse, and in a single project, you don't really get the full beauty of this. Okay. What we'll be doing is we'll have for the Solar Decathlon, we'll want to build a project that's just the API stuff. And that will be its own independent project, and we'll build a jar file, and then we'll upload that to Ivy, and then you'll download the API. And that will be the library that you'll use to build a back end or build a front end and so forth. Okay? And then you'll combine that, for example, with a specific implementation of a back-end database when you actually want to have some persistency. Okay, so I hope you've enjoyed this. I hope you've gotten a little better sense for how to do design with APIs, how to establish boundaries, how to do a little bit of reflection. That's a cool little technique. And implementing interfaces, which might be a little new to you. So I hope you enjoyed this, and I'll talk to you soon.